the working of centrifugal blower. So Dr. J. Krishna is explaining the experiment for you. If anyone is having the voice is a little bit lower, so please make sure that you have earphones with you so that the audio will be balanced, because it is when it is recorded, it is with a very low voice recorded. So I request you to have your earphones ready so that you can clearly listen to the record. Can I go ahead, Gupta sir?
Yes, yes.
So once after seeing the video and audio, if you have any doubts, you can pose your questions accordingly, so that you will get a deep insight into the experiment.
Between fan and pump. Hello everyone. In today's class we will be discussing about centrifugal blower. Before explaining about this experimental setup, let me give some brief details about some turbo machinery and so on. If you just see the broad classification of turbo machines, you can classify it as turbines. Another thing is pumps, blowers, axial fan, compressors and so on. Obviously, the main difference between fan and pumps is that the working fluid, especially in pumps, will make use of liquids like water as your working fluid. If you just see one such aspect, especially if you see the pumps are like fans, blowers or compressors, it adds energy to the fluid. Okay, but in the case of turbines, it extracts energy from the fluid, and finally we can make use of the turbine and convert that thing to electricity. Okay, but here what we do is we supply electrical energy most likely, and through the electrical energy we add energy to the fluid such that the overall pressure or velocity, or in the sense flow rate, gets increased. Okay, by considering these things, let me briefly explain about this experimental setup. This is a centrifugal blower. Okay, here you do have backward curve vanes, forward curve vanes and radial vanes. Okay, but I'll come back to that. What is the physical significance of each and every vane? I'll come back to this. But before that, if you can come closer, from here the electricity is being supplied to this particular meter, because this is a pulse meter. What we'll be doing is we will come to know what is the energy that is consumed by this particular motor. Okay, this will be the actual electrical input. From this, it is given to the motor, and from the motor, by means of a belt, you can see here, this impeller is being run. You can see here, you can come a little bit closer. Okay, so this becomes our shaft power. So this will be the actual energy input. This becomes your shaft power, and power that you get from the blower. Actually, the power from the blower you can get by calculating the volume flow rate. I'll just let you know once I complete these things. Okay. So first let us discuss about different types of vanes. Here, if you just see, this is here internally backward curve vanes are fixed to it. The vanes will be placed like this. Okay, and the movement of the impeller will be in this particular direction. Okay, that means the curvature of the blade is moving in the opposite direction to that of, that means it is moving against to the direction of this, like to what let us take, if it is moving in anti-clockwise direction, and this is towards like clockwise. That is what we can have. To understand in a more detailed manner, this is a forward curve vane. You can see here the rotation is in this particular direction and the curvature is also in this particular way. Obviously, each and everything has its own advantages and disadvantages. I'll come back to this. So this is nothing but your forward. But what it was fitted over there is, it is a backward curve vanes. And that is given a color code. Usually backward curve vanes is coated with black in color. This is yellow, and you do have radial curve vanes. In the case of radial curve vanes, if you just observe, if you can come closer, you can see here it is in radial direction. That means it will be straight. So you do have three types. One is backward, forward, and another thing is radial. So let us see like which one is used for what and so on. Generally, backward curve vanes are much more efficient when compared to that of forward and radial. So now the question comes, why we are using this? Why don't we directly go for backward? There comes the question. Generally, this backward curve vanes will have like relatively it is noisy, and wherever you need relatively high pressures, and efficiency is the most important criteria that you need to consider. You generally go for a backward curve vanes. In the case of backward curve vanes, the flow takes place in the radial direction. But in the case of forward curve vanes, it goes in the tangential direction. The fluid gets pushed in the tangential manner. Okay. So and here what is going to happen is, how it works is, initially the air is sucked in this particular through the center. We call this thing as eye of the impeller. So air sucks in this particular way, and because of this particular rotation, it pushes the fluid and it is actually sent to this particular duct. Okay, now the point is here, as I told, it is much more efficient when compared to that of forward. And if you just see the characteristics of like for all these three vanes, that means backward, radial and forward, if you take the blade angle, in the case of backward curve vanes, the blade angle is less than 90. In the case of radial curve vanes, the blade angle is equal to 90. In forward, it is greater than 90. So now here, what happens is the forward curve vanes are sensitive to particle laden flows. What do you mean by particle laden flows is, for example, consider you have some air which is blown, and in that if you have some sand particles, you call that thing as a particle laden flows. Usually the forward curve vanes are sensitive to particle curve vanes, but radial and as well as the backward curve vanes from low to medium particle laden flows can be allowed. Okay, and as I told, generally what is going to happen is, this can attain relatively high pressures. By the way, like if you just, because this is one of the important point which I am supposed to tell at the starting point itself. If you just see, depending upon our volume flow rate and pressure ratio that is required, we can go for either fan that we have, like it is our ceiling fan. You've already done some axial fan experiment in the previous class, and this is a blower, and another thing is a compressor. So which one is used and when? There comes the question. Generally for axial fans or in fans, usually the pressure ratio is nearly 1.1. It is almost like the pressure ratio is like very small. How do you define pressure ratio is suction pressure, that means at the inlet of the vanes, to that of exit, that means discharge pressure. This is actually the ratio between these two, is actually the discharge pressure to that of suction pressure is nothing but your pressure ratio. Generally for fans, the pressure ratio is around 1.1. And if you just go for blowers, it is nearly 1.2, 1.1 to 1.2. And if you consider compressors, the pressure ratio will be greater than 1.2. Now, what is going to happen? Let us take a basic example of a fan. Ultimately, what we need is, it is to cool ourselves. So, at the inlet, that means at the inlet portion of this particular blade, if you take it as like 1, and at the exit, you get around 1.1. So, but you will, at the inlet and exit, the pressure difference is almost the same. It is, both the things will be usually the atmospheric pressure itself. So, but there will be increase in velocity. So then what about that pressure? Actually, there are certain losses in the blades itself. And there is one more loss when it is actually coming down, there is a down mixing of the fluid. Because of that thing also there is a loss. So usually for our regular fans, there is no increase of any pressure. It will be almost like an atmospheric pressure also. This 1.11, whatever I just mentioned, it needs to overcome that certain losses, blade losses, and even like there are certain curvature effects will be there, and there will be a down mixing and so on. But what is going to happen in case of a centrifugal blower is that the pressure is slightly higher than when compared to that of this fan, and usually it ranges up to 1.2, 1.1 to 1.2. As I told, in the compressor, your flow rate will be much more less, but what happens is the pressure ratio that you can attain will be very high, that is greater than 1.2. So depending upon our application, what we can have is whether to go for lower volume flow rate and higher pressure if we want, then we need to go for a compressor. And in between, like if you want to have relatively higher pressure, higher in the sense, for example, you have some air conditioning ducting system. So for that ducting system, you cannot simply have an opening like this. The air needs to overcome some resistance that is provided by the duct. So if you can go for a centrifugal blower where it can overcome the resistance of the duct and it can reach to appropriate location. And that is why we generally go for blowers in the case of like circulation of the air and so on, where you need to overcome certain resistance. And now what is going to happen is, once the air is taken in like this, it is sent. There is a casing. If you just observe, I'll just give this as like a small homework. Why there is a variation in this cross section of this particular casing? Does it have any significance for it, or is it like intentionally done? So you have to just dig out the answer for it, and it is sent through the duct like this. And here I'll come back to this once I complete the explanation of all things. Here you do have like two probes. This is for, you can see here, this is nothing but a pitot tube where you will find the velocity, and this is a static pressure probe, and it comes out like this, and there is a valve here. So what happens is, you can adjust the, if you can come closer, you can see here there is a valve. You can keep it here actually. Yes. Inside. So what is going to happen is, if you can see, once I am changing this opening and closing of the valve, it gets closed and so on. So what happens is, depending upon the flow rate of it, the load on this particular blower will be getting varied. So we are going to simply adjust the volume flow rate or discharge of this particular fan. So depending upon that, we are going to analyze the performance of this particular fan. So if you can still come closer also, you can see here there is a valve which is getting closed and open depending upon this. So what we have is, we have altogether 1, 2, 3, 4, 5, 6. So this is completely closed and this is totally open, right? Yeah. So this is what we'll be having. And few more important things about like where we can use this forward curve vanes, where we can use this backward curve vanes, is that if you just see this forward curve vanes, you can make use of domestic boilers, warm air heaters, radiant heat tube heaters, and generally refrigerator applications and so on. But especially if you are going for backward curve vanes, you can go for like high pressure condensing boilers, extract ventilation systems, and in the same way fume extraction systems, gas burner systems, and heat recovery systems. You can go for the backward conveys, because as they do have like individual applications and their own advantages and disadvantages. That is why we are going for different, depending upon the application, we need to go for whether for backward, radial, or forward. Okay, in general, if you need to have like point operation, we generally go for forward. And relatively, where the efficiency that is required is more, and we are not bothered about some noise or so, we can directly go for the backward curves. Okay, and obviously when the flow is associated with the particles, that as I told, particle laden flows, forward is much more sensitive when compared to the backward and radial. And from weight point of view, relatively backward is more when compared to that of forward and radial. And radial vanes are much more simpler in construction when compared to forward and backward. Why? Because the stresses that experienced by the radial vanes is relatively less. Okay, this is all some insight about why we are going for backward, forward, and radial. And I did explain you about this experimental setup. So what we are going to do is, let me explain a few things about this pressure probes. If you can come closer, as I told, this through the belt, this shaft is being driven, and as it rotates, the flow will be coming out like this. And if you observe here, there is one mark which is given with chalk piece, which is highlighted here. Usually one probe will be there like this, in this particular direction. So first, before explaining these things, we need to understand what do you mean by static pressure, what do you mean by dynamic pressure, what do you mean by stagnation pressure. These things are required for us. So how do you define static pressure, and what and how this probe will be, is that usually if you just see this probe, if you just consider this as some hole, there is a simple tapping here, that's all. It is a hole which will be smoothened like this, and there is a small hole here. This is a static pressure probe. And now, especially for this, there is one probe that is coming down and it is projected here like this. Whatever this marking is given, one probe will be like this. Okay, so now the point is, before going to these things, let us slowly understand static, stagnation, dynamic pressure. What do you mean by static pressure? So for example, the pressure that is possessed by the fluid, that means you have some fluid particle, and if you are moving along with the fluid, then that is nothing but your static pressure. Then next the immediate question comes, then how you simply keep one small hole, and just how can you measure the static pressure? There comes the question. So usually what happens is there is one relation. If you just dig back your, go back and see your basic fluid mechanics, dou P by dou N is nothing but rho V square by R. Okay. One important thing for measuring the static pressure is that the streamline should be straight. So what is going to happen? When you have a straight streamline, the R tends to be a very high value. R tends to infinity. So dou P by dou N becomes 0. That means pressure remains constant. So that is why what happens is when you are taking a pressure, static pressure, you have to make sure there is no recirculation or vortex formation and so on. You have to make sure that the streamlines are relatively straight. Okay. Now, if you have some flow, it does have static pressure, dynamic pressure, right? So static pressure, if you just take it as a P, dynamic pressure is nothing but rho V square by 2. Okay. Then what is going to happen is now, as you are moving, the dynamic pressure means because of the movement of the fluid, here we have air as our fluid, you do have dynamic pressure. Now here what is going to happen is, if you are actually making the fluid to stop, that means this becomes a stagnant region. Static pressure plus dynamic pressure is nothing but a total pressure. So this total pressure, when the fluid is brought to rest, so this total pressure becomes your stagnation pressure. So if you know stagnation pressure minus this static pressure, you will get dynamic pressure. So now the question comes, why do you need to have this dynamic pressure? So in order to calculate the velocity, because this is a pitot tube, I need to find the velocity. When I am calculating the velocity, I need to have the total head. So I'll just make use of this particular coefficient of discharge, which for it I'll just show the calculation part later. Okay. So once, if you can come closer, first what we need to do is we need to find out the static pressure. In the same way, we need to find out the stagnation, I mean to say dynamic head also. In the pressure or head, you can say in the sense of dynamic pressure or head also, dynamic head. So, or static head. So if you just see here, there are certain walls, if you can come closer here. If this particular wall is inline like this, it means that it is open. If you are turning like this, perpendicular to this, it is going to be like closed. Okay. So now, first what we need to do is, you can see your calculation part, there is a manual which is given to you. In that, you do have a static head as well as dynamic head. So first I am going to explain you about this static head, how to calculate this. So here, even once this college is open, once you come back here, you have a look here. So what is going to happen is, in order to calculate the static pressure, there is 1 close, 2 open, 3 open and 4 close. So what does it mean? So 1 means this particular wall, 2 means this wall, okay, 3 means this wall, 4 means this wall, okay. So here 1 close, that means I am closing this. Closing means I am making it perpendicularly, I am turning this wall in this way. So this is closed means this particular tube, you are seeing this dark color, right? This is closed, right? This is closed. Now this should be 2 is open. That means to this particular U-tube manometer, whatever you are seeing, here this manometer liquid is water, right? So this, if I am turning this, 2 open means this particular manometer is open to atmosphere, this particular liquid level, okay? Now 3 open means I am opening this one. Opening this one means, if you can see here, this is, as I told, it is only a static pressure probe. That means you don't have any projection also. It is like having a hole like this, and if you take this as your pipe, and to this pipe, this probe is laid like this. Okay, so it is something like this. I hope it is clear to you. This, if you take this as your wall, so you can see here this wall, this small hole will be there like this. So now this is open. This is open, and obviously this is open means the 4 should be closed. So close means you turn it off. So now this is closed, that means this is open to atmosphere, and I did mention this is the only one small opening is there, this is nothing but a static pressure. So this is open here and this atmosphere is closed. So when you do this kind of arrangement, whatever you get is nothing but your static pressure or static head, right? This, then what we do is when you are switching on this particular experiment, it will run because depending upon how much opening or closing you are doing, you are actually, let us take you opened partially or fully, then you do this kind of arrangement and take the reading. That will be your static pressure. So if you can see this particular manual which is actually given to you, there are certain things. This is the static pressure. Okay, so this is what you will be doing here. Already these readings are taken, which will be circulated to you. So this particular part first, with this arrangement, you will get this static pressure. Next, what you need to do is you need to get the dynamic pressure. So in order to get the dynamic pressure, what kind of arrangement you are supposed to do is, see, one is open. So one is open means I am opening this, right? So this is open. Now see here, one is open. So this, the bottom portion is 1. Now 2 is closed. I am just closing this. That means whatever this YouTube manometer you have here, this is not open to atmosphere, but it is open to the probe that you have here, right? This dark tube you are seeing here, right? Now this is open. But in the previous case, it is closed. Now whatever I am trying to do, I am trying to find out the dynamic head. So for that, that is why this is open. Okay, this is open. So this is your 1 open, 2 close. That is what I did. Now what is going to happen is 3 is close. 3 means this one. I am simply closing this, right? And whatever head that you get here, okay. Now this is open to atmosphere. Now directly you will get the stagnation pressure out of it. So once you take out this stagnation pressure minus, it is like now here 3 is close. 3 is close means this one, and 4 is open. Yeah, sorry. So this is like, this is perpendicular to it, as I told. This is closed now, and this is open. Okay, I hope things are clear. Now the point is, once you get the stagnation pressure, and previously like you will get the static pressure, to this, from this directly you will be getting the dynamic pressure. So dynamic head you will get. So dynamic head plus static head, you will get the total head. You will make use of the total head. Already in your manual, these details are given to you. Just let me discuss with you. So you will see this this total head. You do have row of air and row of water. What does it mean is, this is static head and this is dynamic head. Why? Because in the manometer you are using water as your working fluid, right? No, sorry, like water as your manometer fluid, and air is your working fluid. So in order to have an appropriate head, obviously we will make use of this conversion factor. So directly you will get in terms of like air, because air is your working fluid here. Now once you get the total head, you will make use of the total head to calculate the velocity. How will you calculate velocity is, C square root of C is nothing but coefficient of discharge. Usually it is taken as 0.98. And the fabricator, whoever supplied this equipment, has given that coefficient of discharge to be of 0.98. So 2g into h here. Okay. So from this you will calculate the velocity. Once you get the velocity, you know the diameter of the pipe, area pi by 4 d square, because it is a circular cross section, into its velocity, you will get the discharge. Once you know the discharge, okay, discharge into head into density, but obviously I am converting everything in terms of HP. Okay, so that is why you are dividing by 746. So you will get now the power of the blower, right? So that means from the blower, what is the power that you are getting? From next, what you need to do is you need to calculate the blower efficiency. How do you calculate blower efficiency? Power of the blower divided by power available at the shaft. So usually what is going to happen is, the power is given from the meter, that means electrical supply is there. From the meter you are running a motor, and from the motor you are connecting to the through the belt, and this belt is driving the shaft. Okay, but what is going to happen is, usually we do, you need to calculate the curves. From that you need to calculate the efficiency of this particular motor. But what we do is, here generally it is assumed as, please check the details that are given to you. I think it is 0.8 or 0.9, take an appropriate value. Okay, so you can take around 0.8, so and just calculate the power of the shaft. And how do you get the power that is supplied through this electrical power input? That is the actual power that you are giving from the through the motor. So this power you can get by P. P is nothing but number of pulses. Okay, and the time taken to attain that many pulses, and EMC is nothing but energy meter constant. And in this particular case, energy meter constant is nothing but 3200. Okay, and you are directly converting everything in terms of HP. So once you know what is the actual electrical power input, this becomes your denominator, and what is the blower power, you will get the overall efficiency, because you need to plot this overall efficiency also when you are plotting three graphs. Okay, and one more thing is that blower efficiency is also there. That is nothing but the power that is available at the shaft, and in numerator you have power of the blower. So with this you will actually get the blower efficiency. In this particular case, as we are taking the efficiency of the motor to be around 0.8, you will have blower efficiency curve and overall efficiency curve to be almost in the same manner. Why? Because we are actually taking this efficiency to be of same value. Okay, usually in this particular case we can take around 0.8, and obviously what happens is it depends upon the supplier also, we need to take the appropriate value. So in this way all the details are given to you. I hope it is very clear, and all the other, what is the area of this particular duct is already given to you, and G is given, energy meter constant is also given to you. This is a manual which is supplied to you. Okay, and the nomenclature, like what does each and everything, is also given in the manual itself here. So this is what you need to do, and you need to draw two curves. One is head versus discharge, and one more thing that you need to plot here is that one is total head versus discharge volume flow rate. You need to draw curve depending upon what readings you got, and another thing is overall efficiency versus discharge. So this is what you are supposed to do for this particular experiment. I think that is clear. And one more thing, this needs some basics of fluid mechanics also. Try to go through basics of axial fan, blowers and compressors also to get more insight about this. And please do go through these forward, backward and radial vents and try to understand where we are using and for what purpose we are using. Thank you.
So any doubts up to this? Anywhere you want to relook at? It's the same experiment what we have done for an axial fan. Same, we are measuring the input, we are finding out the static pressure, dynamic pressure, and then we are calculating the efficiencies.
Sir. Hello.
Yeah.
Sir,
Yes.
while calculating static and stagnation pressures, we are using atmospheric pressure as the other side, no, sir, like other side of manometer.
Mhm.
We are, it's open to atmosphere, right, sir?
Yes, it is open to atmosphere.
So while calculating the pressure head, we should also add a atmospheric pressure head or not, sir?
Can you repeat the question once?
No,
Not
I
sure.
mean, like if we got 1 centimeter difference while measuring the static pressure, we
1
should,
centi.
I mean,
No,
some value, H value, we will get, no, sir. From graph, we will mark on the graph and we will find the manometer fluid difference, height difference.
yeah, we will find the height difference. Correct. Correct.
And while calculating the pressure, total
Okay.
pressure in atmosphere or pascals, while doing that, should we
No, no,
like
no. There are
add
two ways of.
atmospheric pressure also or not?
No, no, you need not add atmospheric pressure because we are actually finding the differential pressure. See what you are getting out of the this in this particular experiment. Have you understood how the walls are connected?
Yes, sir.
Yeah.
Yes,
So
sir.
in one case, in the light tube that you are seeing over here, for example, whatever the light tube.
What do you mean by static pressure? Use this forward curve when
So here,
blower is that the pressure is
See here, this one. Are you seeing my?
Yes, so that is
cursor? Yeah, this thing will go into the tube, and the other side it will be atmospheric pressure. So whatever the height that you are getting, it's nothing but atmospheric, correct? So it's a differential pressure that you are getting.
yes, sir.
So
That
that
height
means
will
it is a
be
gauge pressure. That means it is not
yes, sir.
vacuum. With reference to atmosphere, how much above it is. That is what you are finding.
Yes,
Why
sir.
do you want to add it? Because it's not an absolute pressure, right? Whatever you are measuring
Okay.
is a gauge pressure.
Okay,
Clear?
sir. So we will take gauge pressures only everywhere.
Yeah, that's what we will do because everywhere air is present. So obviously you have to take gauge pressure. Unless there
Okay.
is some kind of a suction or those things are there, vacuum pressures are required. Otherwise, you will always take gauge pressures into account. Never, in general, you will never use the what we call absolute pressures. Any more questions? So I hope you understood the whole procedure. I just want to repeat the same things. It's like we are giving from electricity, we are running the motor, and from the motor we are running the blower. So as sir has explained, blower gives much more a higher pressure difference compared to a fan, axial fan, what we have seen. So in this, all the procedure is same. In the earlier experiment, which is axial flow fan, we are having a butterfly ball that is moving 8 revolutions. It closes the opening or the exit. So by controlling the amount of air that is leaving through the exit, we are actually calculating the different mass flows. Here also we have another mechanism where we have this valve procedure which is shown at the end. So through that you are actually trying to find out we are trying to vary the mass flow. Both are same. So a valve position. And then there also you found out the valve, you are trying to find out the static pressure and dynamic pressure. Here also you are trying to measure both the static and dynamic. Okay, so here you are having the pitot static tube. That is what is mentioned over here. So when you want to have the pitot static tube, you will directly with the manometer. This manometer this U tube has to be connected only through these pipes. That's why the other two walls, which are related to this and atmosphere, is closed. And when you want to measure the static pressure, the pressure valves that are going to the manometer by suitable valve mechanism. So we are closing the valves which are taking the pressure from this pipe, and we are opening the valves which are related to this particular pipe as well as to the atmosphere. So that is what 1, 2, 3, 4. If you are directly viewing that, you will have a better understanding. But for the time being, you understand that when you are trying to open the dynamic pressure, only the pipe connections are open and connected to the U-tube mount. Whereas here, in the second case, where when you want to have static pressure, the openings are the flow the pressure that is coming to the U-tube manometer through the bypass walls. Those two walls are closed, and only one wall coming through the pressure that is coming through this wall, as well as the height of the other side of the wall, other side of the U-tube that is open to the atmosphere. So that wall we are open. Apart from that, all other, in the earlier case, there's two different U-tube manometers given. Here we are having the same U-tube manometer with bypass walls. That is someone is asking.
Sir,
Yes?
while we are calculating dynamic pressure, sir, both atmospheric valves are closed, right?
Yeah, correct.
Yes, sir. Okay. That's what I want to clear.
Okay. Any more questions? Otherwise, if you understood, so what we are trying to do is at the end we have that valve now. So we are trying to keep that valve at different positions. That means completely open to the completely closed positions in certain intervals of opening. We are trying to operate the centrifugal blower. And from that, we are trying to find out what is its static head, what is its dynamic head. And from that, we are trying to find out the discharge or mass flow rate. And from that, you are trying to find out what is the blower efficiency. So from this, what you will be able to find out is you are using the electricity to get out to push the certain amount of fluid. So where you will get the maximum efficiency. So just by increasing the electric input, are we going to get more mass flow rate, or it will vary? Or we have a certain position where we get a maximum and then it becomes lower. So that's what you need to actually look at. Okay, you need to understand. So that is what the experiment is all about. Other thing is you also have to answer some of the questions, and today I went to the lab, but unfortunately I couldn't get the manual. Just give me some time. I will upload that manual into the drive. So please keep on checking that. Meanwhile, you can use this. I will supply the recordings, readings to you. So basically, from this video, you have the equations. Up to that point of time, you use this. Or tomorrow, by tomorrow, your manual will be in the folder shared with you. So that is what I want. Okay, if everything is fine, I will try to show you how we are going to take the readings. Before that, you can just watch some of the things that are there. So you can see here, this is a pitot tube, what sir has told you. Okay, so this is the flange, I think. So when the flanges are flitted, you have, after the flanges, you have the static. Okay, this is one. Second, so this is the opening. This is the static. Okay, the other side of the it is open. You can see here. Yeah, this is the light colored, so only smooth open. This is for the static. This is for the dynamic. Okay, this is for the dynamic. So when these flanges that I am showing here, so those are actually connected with the help of the screws, and then therefore it formed as a single tube. Okay, so this is the forward vents I was talking about. So the direction of the blower, so it is in this direction, and the blades are also in the same. This is the radial vein where the veins are straight. They are not curved. They're not curved. They're straight. And this is the backward vein, which is what actually we are finding the characteristics. So this is the how the veins are. They are curved, but the direction now is in this anticlockwise. Okay, so this is how the blades will be inside this. Okay, so you can, just to show you the blade structure, you can see here. See, the blade is curved like in this direction. Okay, just give you a feel and see this. Any more questions? You can quickly ask, or we will see. This is what they have opened the top shelf to show the inner impeller, how the shape of the impeller is. So if you don't have any other question, I will forward with the how they are taking the limits. You can see those limits. Okay, I will supply the values, numerical values, but meanwhile you just can see how they are taking the limits. The first thing is they have to give a particular opening at the end of the tube or at the end of the exit of the pipe, and then they have to measure how much input they are giving, how many pulses, for 5 pulses or 10 pulses, how much time it is taking, that they will record. And then they will, by suitable openings or by suitable arrangement of these bypass walls, they will first find static pressure and then dynamic pressure. So will note it down, and then for each different position of the valve at the end of or at the exit of the pipe, for different positions of the this valve, they will find out certain readings, and from that you are asked to see how the performance characteristics of the centrifugal blower is varying. If you don't have any further questions, I will try to play this particular video, which shows you the working, how we can take the readings of the experiment. Any more questions? Please feel free to ask. Gupta sir is also there. We will also, so the more the questions, we will get more knowledge. So we will have an expert in the field, so you can also ask some questions.
Sir, can the veins be used in reverse order? Like if we have forward curve veins, if we keep it in, is there a provision to keep it in reverse and use it as reverse curved veins?
If you want to have, you can have a mechanical arrangement which can be tilted this way, that way. You can change it, but we don't have that here. We have separate impeller for each type.
Okay, sir.
But why do you want to vary that? There should be certain reason. No? What is the reason you want to have? They have tested it and they said that it is much more efficient, right? So what is the reason?
Like
Well,
if we have forward curve vanes and suddenly due to some environmental problems, there is like dust is going. As you told, as sir told, the forward curve vanes are sensitive to dust, I mean particulate matter. Then if possible, they can use backward curve vanes instead, like that.
all right.
Okay,
Okay.
mainly forward curved vanes are very rarely used and almost not used practically. Okay, backward curved vanes are used for industrial purposes and radial vanes are used for aircraft purposes. Right, forward curved vanes, it is just theoretical interest. We are putting that what happens in that way. Theoretically, it gives pressure rise when the flow is increasing, pressure ratio also will be rising, which is against nature's law, right? So it gives completely unstable operation. So we normally never use the forward curved vanes. For industrial purposes, we use backward curved vanes. For aircraft purposes, we use radial vanes when there are high speeds. Okay, that's it.
Okay, sir. Thank you.
So what I understood from his question is he wants a
No.
mechanism so
What
that
he is telling is sometimes according to the flow conditions, if we want
yeah,
to
that's
change
what
it,
exactly. Can we change that? Is there any
that's what he is
mechanism that
asking.
that's good question. Any more? Okay, then I'm going to show you the second video where we will be looking at procedure for taking the readings of this present. This is the opening, so they will have 5 readings. The current position, it is completely closed. You can see here there is a numbering given. 1 is this, 2 is this, 3 is this, and 4 is that. So likewise, they have numbered already. It's common sense that which way you are connecting it. So from that you can do it. For simplified thing, they are mentioning it as 1, 2, 3, 4. The simple case is they have the bypass walls which are connected to the U2. So whichever tapping from whichever tapping you want to have the pressure variation, you will connect it. This is kind of taking the readings for static as well as time. So if you observe here, the electric meter is slightly different from what we have seen. There is some blinking that is happening. So through the pulses, how many pulses it is taking through that? When we take. So there is pulse coming, red color. Yeah. Let's see. Okay. So for different positions, we will take different outputs. So the experimental speed. Okay, I hope you have understood this. Any questions? Now, I would like to share the readings. You can have a look at it. You can take down the readings if you want. Okay, CD value is given. So I'll keep this readings in the same folder. Just give me time. I will put that manual also. Today, if you are not able to find that manual, just
Sir, I have some manual, sir. Can I
you
share?
have.
Yes, sir.
Sure. If you have, you put that to my mail. Dr.
Okay.
Sam at the rate of Dr. Dr. Sam. The rate of
But let him put in their group also, I think.
Yeah,
everybody.
if I share that in the folder, sir, already that folder which is in my drive has already been shared. So it's the same, so they can see whenever they want.
Okay.
So any more questions, please ask. Just once it idea. So one question I can ask you is basically related to the experiment. Where can it go wrong? Just a minute. This is from where you got? From our lab only?
No, sir, previous year, some drive.
This is this one. Yeah, same thing. Anyways, I will try to find. I told the person to bring. I will send them. This was same thing. Static was a bad time taken. It was the same thing. But you take a neat photograph and share it. For the time being, you can use the same. What is given? It's all the same. Any more questions, guys? Any more questions? If you have no questions, then I'll try to find a session with Professor permission. Professor, can I we stop the
Oh, okay.
sessions here?
Okay.
So by tomorrow, you just have a look at your folder, which is shared with you, and make sure that it will be there within the readings also I will share with you. Anything more? Okay. If you have no questions, no queries, today's session, I want to close today's session. And one more important information is that in the first meeting itself, sir has Dr. Professor Ambaprasad sir has explained you that we will have 3 skill tests. Okay, so Viva kind of test. Already we have completed 1 test. So next week, 4:30 to in between 4:30 to 5, we want to conduct 1 more test, and the following week also we will have another test. Next week test will be on the 4 experiments that you are conduct or that were conducted in the second cycle. And the last week experiment will be last week, the following week, whatever exam will be having, that will be for the remaining set of experiments. Okay? So first cycle is done. Second cycle, whatever the experiments that we have, we will have that on that you will be having the. It's like the same format and all are same. Only thing is you have to slightly know how you are carrying out the experiment. What are your outputs are, what you infer from the experiments. Those things you have to be well versed. Apart from that, the exam pattern, everything will be the same. And I will send you through a message if any changes, okay? Or I will vent it out through your CRs if anything. Both Sarthak and Kalwar, through them I will share whatever information is. So please be prepared with the experiments. After the first 4 experiments, whatever has happened until today, we will be having this last week, until last week, we will have that for the exam. This week and the following 2 weeks, integral Boyer, and the next week, whatever we are going to do, that will be there for the last week. Clear? Until last week, whatever has happened previous week, that will be there for the exam. Second skill test. Okay, clear?
Yes, sir.
Okay. Okay, then I'll stop the video session for today.
Okay,
Thanks
see
for
you
attending.
guys.
Thanks for attending the session, all of you. Thank you, Gupta sir, for joining. Bye. Take care.
Thank you, sir.